Very often in engineering, we have to rework existing designs. This might be because the design is for a new client or for a new job, needs rework, or is simply a catalog-driven part built to order. Here's an example of such a configurable design. It's a sheet metal box. It's very simple in its construction. It has some vent holes, some handles, and a frame, but it's designed in a very special way. By manipulating these input parameters, we're able to change the geometry of the box. So I can change the width, the depth, and the height here. Click apply, and we can see that the box becomes larger. The number of vent holes increases and they remain distributed. We can also alter it in other ways, such as changing the thickness of the base plate, reducing the thickness of the sheet metal, changing how the handles are oriented, and removing the vents. We can even get rid of that frame at the bottom. Such configurable designs are called configurators and are designed using parametric designs coupled with iLogic. In this demonstration, we're going to have a look at creating an iLogic model in Inventor. We're going to start our configurator with the base model. Here we're going to go into each of the parts and implement parametrics into each of the parts so that they can be easily configured. Let's start off with the lid. Here we have the lid, and it's a regular sheet metal part with patterns that produce the vent holes. So what we want to be able to do is manipulate the length and the width of this lid, as well as manipulate how these vent holes are distributed and whether or not they're even included in the model. So let's get started. If we look at the face, here we've got the sketch from which it's based. We can see that the width is 300 and the length is 400. These are dead parameters at the moment. Parameter D1 is equal to a static value of 400. Parameter D0 is equal to a static value of 300. Let's go ahead and create new parameters. We're going to create a new parameter called length and another parameter called width. And here we can put in values. We'll put the length as 400 and the width as 300. Next, we can come into the sketch, and rather than putting in a static value, we can say this value is equal to the parameter width. For this one, we can say is equal to length. Now, we'll find that whenever we change the parameters, the sketch will update and the consequent features will also update. So, as we can see from our manipulation of making it longer, the vent pattern started to break. So let's go ahead and look at that one next. Let's go into the vent feature, which is this rectangular pattern, and have a look at what makes it up. We've got two rows equally distributed along this length, 344 millimeters. So what we're going to have to change is this. We're going to have to put in an expression that changes with respect to the length. So rather than a natural value of 344, we might say equals length minus 2 by 28. So now, no matter what we change the parameter length to, the vent holes will distribute themselves evenly across it. However, as we make this shorter and shorter, the vent holes have come closer and closer together, and that's not acceptable. So we're going to have to put in another parameter that will govern how many vent holes actually do get included. So to do that, we'll come along to add a numeric feature, add a numeric parameter, and this time we'll say number of holes. Now, because it's a number and not a length unit, we're going to have to change it from millimeters to unitless, UL. And we'll change it to 8 for the moment. Next, we'll go into the rectangular pattern that makes up the vent, and we'll change it from the static value of 8 to equal number of holes. Now, that doesn't address the issue because at the moment, the number of holes doesn't change as the length changes. We could, if we wanted to, include an equation in here, but I'm going to do it a little bit more difficult. Let's go to the iLogic panel here and implement a new rule. Here, we're going to create a new rule, and we're going to say update vents. So here, we can manipulate the value for the number of holes. We can say the number of holes is equal to the length over 50. And now, whenever the parameters are updated, we'll find that the number of holes increases along with it, or decreases as is needed. There's one final thing. In our original configurator, we had the option of including or excluding the vent holes themselves. So we're going to have one more parameter in here. It's going to be a true-false parameter, a Boolean, and we're going to call it vents enabled. By default, it's true, and we're going to update our iLogic rule. Here, we're going to put an if, then, and else statement. So we're going to say if vents enabled equals true, then we will enable the two features that make up the vents. If that's not true, so else, then we will turn them off. So what this does is it disables the vent holes if vents are disabled for this part. So we'll save and run it and test it out. Here we can change the vents, turn them off, and turn them back on. Wonderful. So that's the lid. Let's move on to the other parts. So this time I'm going to quickly flash past and see if we can do it very quickly. So next we're going to go into the box itself, and we're going to create the parameters length, width, height, and give them values 400, 300, 130. We'll quickly go into the sketch and replace the static parameters with our new parameters. So we'll say that's length, this is width, and the flange height, which makes up the height of the box, will rather than be equal 160, equal the height. Beautiful. Okay, so this one's a little bit trickier because depending on if it has handles or not, the vents on the sides will disappear or appear again. So we'll save our progress, and we're going to create a couple of more parameters. So we're going to create a new parameter called handles handles. And it's not going to be a true false. We'll change it to a list value, so text value, handles. Now, the handles can either be lengthwise, widthwise, or none. And by default, it's going to be none. So next, we're going to go over to our add rule. We're going to manipulate our rectangular patterns, and let's change these static values. We might say that the length of the pattern is equal to the length minus 2 by 28. The length of this pattern is also equal to width minus 2 by 28. Now we have to go back and change the number of holes. So we can say add two new parameters. The first one is number of holes lengthwise, and another number of holes widthwise. And we'll change them both to unitless and change it to 11 and 8. Now we can go into the patterns and say equals number of holes lengthwise. Here equals number of holes widthwise. Lovely. Oop, it seems to be a bit off center there. Oh, right, because the number of holes is supposed to be an even number. There we go. Odd number. Wonderful. Okay, so far so good. What we need to do is include some code that will update the number of holes, but also disable the holes should there be a handle on that side. We'll skip the portion about adding more or less vent holes, but instead just create a rule that updates the geometry based on where the handles are. So we might create a new if then else statement, and grab our handles parameter and say if handles equals none, then, and we'll disable all 4 of the features that make up the vents. Wonderful. Next, we'll have to say if handles equals lengthwise, then, and turn on the handles lengthwise. That is to say, disable the patterns that are lengthwise. Might just rename these features to be more convenient. Lengthwise and lengthwise. Wonderful. And get rid of all of the bits of code we don't need. If it's not lengthwise or none, then it must be widthwise. And therefore, we can have else. It will turn on false. There we go. So this enables and disables the features depending on what value we choose for the handles. So we'll say if it's lengthwise, then the vents will be in their position, and if it's widthwise, it'll be in the other position. Although I have booked this and I will change it very quickly. False, 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 false. True, 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 true. Wonderful. So if the handles are lengthways, then there's no vents on the length. And if it's widthways, there's no vents on the width. If there's none, there's no handles at all. However, there's another parameter that we've got at the top level, which governs whether or not there's vents at all. So we're going to have to make another, and we'll say, call it vents enabled. And by default, it will be true. And what we're going to do is turn this into a nested if statement. It's going to start off with if vents enabled equals true, then do the regular thing. However, I'll just add that in. If the vents are turned off, then just turn off all of the vents unconditionally. And if. Lovely. So here, if the user decides, yep, we're not using vents at all, it doesn't matter whether it's lengthwise or widthwise, it's going to switch them off anyway. Wonderful. So there we have the lid and the body sorted. What we're going to have to do next is create a new level of detail. This is because we are going to enable and disable these handles depending on whether the handles are lengthways or widthways. So we'll create a new level of detail, and we're going to call this level of detail iLogic. Now, for the start, we are going to suppress the widthways. We'll just rename this to be convenient. We'll say lengthwise 1, lengthwise 2, and this one will be widthwise 1 and widthwise 2. Wonderful. So as I can see from the current configuration, we've got a lengthwise configuration for the handles. So we might disable the widthwise handles by right-clicking and suppressing them. Looking good so far. Okay, so what we want to do is give the user the ability to decide what the parameters are and to have the geometry update accordingly. So here we'll come to the assembly level parameters and create a bunch of parameters. So we'll have our typical ones: length, width, height, and handles. But the handles, rather than being a numeric parameter, will be a text parameter, handles, with the values that we give it here. Lengthwise, widthwise, none. Next, we'll add in a true false and say vents enabled. They don't have to have the same names that we've used for the parameter in the child parts, but it helps in the programming, as we'll see. Enabled. Okay. So what we're going to see is that these parameters don't do anything or mean anything. We can change them and nothing changes because they're not being fed into their child parts. So what we're going to do is add in a rule that forces children to update accordingly. For the moment, I'm just going to suppress these components. Actually, no. Before we continue, let's go ahead and add in some parametrics to this. So here we've got a sketch that governs the frame at the bottom. So we'll make a parameter called width and another parameter called length and give them the values that we're used to. As before, we'll go into the sketch and we're going to say that's equal to length, that's equal to width. Okay. And there we've made it parametric. I'll do the same for that mat in between, the base plate. And here I'll go ahead and make new parameters, length and width. Oops, 400, 300. And here we can put in our parameter name. So I'll say length and width. Wonderful. We're nearly there. Excellent. Save. Okay. So all that's needed now is the ability to give for this assembly to feed parameters into its child parts. So we're going to make a new rule and call it update geometries. And here, the first part is going to be very, very simple. We'll just grab the parameters of the child parts and we'll assign them to the same length and width as the assembly level parameters. And we do this for each of the parts. It's very straightforward. So we say length, width, height, handles, and vents. You might notice that we skip the number of holes lengthways and widthways. That's because it only matters internally in that part. Whereas these parameters are fed to it by the assembly. Grab that and grab that. Height, handles, and vents enabled. Continue doing it for each of the parts. So we'll say body, lid. So the lid is next. Here we can say the user parameters length and width and vents enabled equals these values. Beautiful. And frame. And the final one is the frame. So we'll grab the length and width parameter for the frame. And there we have it. So it's nearly done. So far, what it's going to do is grab the parameters from the assembly level and feed them into the child part. Let's see if it's working so far. So we'll come to the parameters and we'll make the box longer and wider. So we'll say 600. And there we can see it's longer. So we've fallen into a trap. The parameter that governs the length of that frame at the bottom was misassigned. So we're going to come in here and edit the sketch. And all we need to do is change these around. So it turns out that this was the length and that this was the width. Say finish, save, and now we can see that the part updates appropriately. We'll try that one more time. So we'll say 500, and we can see the part becomes longer and shorter accordingly. So far, so good. Ooh, we changed the width, and that pattern didn't follow along. So we'll go along into this lid, and here we'll come to the pattern that makes up the vent holes. Here, we're going to replace the static value for the width of the pattern array to equal the width minus 2 by 28. And now it should follow along nicely with the width of the box. So we'll make it long and narrow. So at the moment, we can see that we can change the handles orientation, but it's not changing the handles in the model. So we need to change. We'll just check and see if the vents work. Yep, wonderful. So the last thing that we'll do is make it so that the user can assign where the handles are. So we're going to have to go back to our iLogic rule, and we're going to put another if then else statement. So we'll say if handles equals lengthwise, then, and we will grab these handles and make sure they're unsuppressed. Else, if handles equals widthwise, handles equals widthwise, then we'll grab these and we'll make the opposite true. And if it's none, then we will disable all the handles. Lovely. Let's see if it worked. So here we'll come along to our parameter list. Here we can change it lengthwise, widthwise. Looking good. We can turn on and off the vents. And we can also change the parameters that govern the geometry of the part. So there we have a configurable model. There might be one last stage that we have with this 3D model, and that's to give it a more digestible way of editing the parameters. So far, we had to go into the parameters list, and there's no limits on what we can input here. So what we might do is create a form. Here, we can make a form. We can call it edit box, and make it so that the user has to assign, say, apply to make the constraints. So let's say, okay, cancel, apply. And here we can drag in our parameters: width, length, height, handles, vents enabled. We could here manipulate the parameters, but in many ways, this is absolutely no different to what we had in the parameters list. What might be nicer is if we have sliders and limits. So we'll come in here, and we're going to edit the length parameter, and we're going to give it a slider. Its minimum value is going to be 200, and its maximum value is going to be 800, with a step size of 50. We're going to quickly do the same for width and height as well. So we'll say here it can be from 200 to 1200, no, 800, with a gap of 50, and the height might go from 40 to 360 with an increment of 10. Handles will be a combo box, and vents enabled will be okay. Now we've got a form that any user can manipulate within the limits. So you might turn it back to its original configuration, 30, change the handles to lengthwise and disable the vents, click apply, and we'll find that our model automatically updates. So see, making a configurable model in Inventor is really very simple when you know how. That was a demonstration on how to create a configurator using iLogic in Inventor.